Energy is amazing. It is so amazing that in one moment of time, everyone on Earth uses a combined total of 18 trillion watts. That's a whole lot of energy. So let's scale this usage down and ask ourselves how much energy would it take to throw a baseball to the height of the CN Tower? And to make things simpler, for this question, we will assume that there is no air resistance. Firstly, we know that the weight of a Major League Baseball is 145 grams. Earth's gravity at the CN Tower is negative 9.8 meters per second squared, and the height of the CN Tower at the very top is 553.3 meters. This is all the information that we basically need to know to find the kinetic energy required to throw this ball. The formula we will be dealing with is kinetic energy equals 1/2 of mass times initial velocity squared. But in order for us to even use the formula, we need to find initial velocity, which we will use one of the big five kinematic equations. Final velocity squared equals initial velocity squared plus 2 times accelerations multiplied by distance. Once we plug in the given information, which is final velocity, acceleration, and distance, our equation will now look like this. Next, if we isolate the formula for initial velocity, we can calculate it, which comes to 104.14 meters per second. We now know all the information to solve for kinetic energy. Again, if we substitute all the known variables, we will find out the required energy to throw this ball. And the answer is a whopping 786.2 joules of energy. That is about the energy created from firing a pistol, except a bullet is only a fraction of a baseball's mass. Now, to put that into a comparison, the fastest throw from an MLB pitcher is 105 miles per hour, or converted to 47 meters per second. But when we plug in 47 meters per second into our energy formula, we will only get an answer of 160 joules. That is almost 5 times less. So it is very unlikely that a human being can throw a ball to the height of the CN Tower. Now, let's ask ourselves, what is the maximum possible height that a baseball pitcher can throw, assuming the velocity of the throw was 47 meters per second, which is 105 miles in our terminology, when it left the pitcher's hand? Again, we plug all our known variables back into our kinematic formula to solve for distance, and the answer is the ball would only go up a mere 112.7 meters even if there was no air resistance. Questions and calculations like these are the key to understand how the world works around us. Understanding motion itself can help us excel at anything from engineering to sports. If we didn't have physics, our world would look nothing like what it did now, and we would all be blind to the wonders around us.